Well, hello. Um, Today I'm going to be talking to you about Lab 2 and specifically the Simulink model, and we're going to start by just sort of looking over what an end model will be, and then I'll show you how to create it. So first off, we have a couple different elements here. So on the far left, we have the signal generator block. If we were to open that up, we have the option to do multiple different waveforms, as well as change the amplitude, the frequency, and a couple of other settings. For the offset, we're going to be just using this constant block where we have the input at a constant value. We have these summer blocks, which just add the signal and output it. We have a PID controller block, which we're setting into the PI control mode. And then we can control different parameters. So in this case, I'm going to set it to 0, 1, 1, just for standard pure integral controller. We have a saturation block here with different limits. We have the transfer function which represents the plant. We have a white noise generator here, which we've set to 0, but we can use that to test the robustness of the system. There's a pulse generator. This is to simulate disturbances affecting the system itself. These are called multiplexers, and they're used to just sort of connect the signal in so that when you go to the scope, we can see more than one at a time. So this nice response here was from the train controller that I was using earlier, and then here is a pure integral control response. So the next step, I'm going to be walking through how to create a Simulink model, and specifically what went into developing the Simulink model I just went over. So if we open up a MATLAB file here, we can start by going to Simulink, which you might have it someplace else up here, but we have to go back to Home and open Simulink. In our case, it'll pop up, and we just have to select a blank model. So once we have a Simulink model open, we can do a couple things. Normally, I just already know what I'm going to be assembling, but if you know all of the blocks you're going to be putting in there, you can start pretty simply. So for instance, if I were to just double click, I can start by typing in a PID controller. We want the PID 2 degree of freedom controller. And then within this controller, what we're going to be doing is we're actually going to be setting it to a PI controller. That way we have those 3 parameters that we're planning on tuning for this lab. Another block we're going to be needing is a transfer function block. There's a lot of different ways that you can create this block, but in this particular case, we will be using the setup where we just come in and type up the coefficients depending on what we want the block to look like. So in our case, we're going to be doing the k value divided by tau, and that's just going to be a signal gain, first order. And then on the bottom, for the S term, we're just going to be having a 1, and then we have 1 over tau. So those will be your values. Making that a little bit bigger so you can see what the transfer function is there. In between those, we're actually going to be putting a saturation block. And this saturation block is going to have an upper limit of 12 and a lower limit of negative 12. Just connecting those 2 blocks. The next block that we're going to be needing is we can start in different ways. Again, it doesn't matter which order you go. So I'm going to go back here and start with the signal generator. And this block's pretty generic, but we can set it to a lot of different things. In our case, we're going to be using a square wave most of the time. I'm just going to set it to an amplitude of 50 and a frequency of 0.5 hertz. Sorry, should have mentioned. Do make sure that you have it in the hertz so that this output is based in seconds. We're also going to be using an offset, which we do by creating a constant. In our case, we're just going to set that to 100. It really depends on which section of the lab for each one of these particular blocks. We're going to need a sum block. In this case, the standard 2 structure will be fine. I'll show you how to change it when we go to the next one. on the other side, but this is just going into the ref signal. Let me just make it look a little bit prettier. The next block, I guess, would probably be the other sum block. So within this sum block, we're actually going to need a different set of signs. We're going to need 3 signs. So we're going to do 3 pluses. You can do a subtraction if you want. But as you can see, since it's in a round configuration, we'll come in the top, front, bottom. On the top, we're going to have a white noise generator, band limited white noise. And just set it to a power of 0 for now. We probably won't be using it when testing this lab, but it is very nice to have if you want to check the robustness of your system. We'll be doing a pulse generator, and this determines, we're setting it to 0, but this determines a lot of things when you're trying to put your disturbance into the system. It's nice to have a pulse that we can control the length of it as well as the amplitude. And then at the end, we're actually going to need a scope. And for this one, we're going to need 2 inputs. And we'll come back in here in a second. We're going to need, another thing is 2 muxes. So these are just 2 inputs on those. And I'm going to duplicate it. And again, there's a picture of what the Simulink model should look like in the book, if you want to be able to take a look at that. In this case, we're going to have our omega up here, coming back to look at both the reference signal as well as what the omega currently is. We're also going to need to take the feedback loop here, being the current position, being fed back to the PI controller. This mux here is going to look at the signal coming from the saturation block, on both sides of the saturation block. That way we can see what the control effort is originally, as well as how it is adjusted when the saturation is applied. And then we can take these both outputs and throw them into the scope. And this is really the basic setup. Throughout the lab, I will be making different statements about how to do each individual setting and what the settings should be. But for now, let's just set it to the defaults. So going through the lab procedure, we know that we have an amplitude of 50. This could either be 1 or 0.5. I have it set for 0.5. The reference signal, setting it to 100 as a default. Again, these change a lot. The PI controller, we're going to start with just the proportional only controller. So throw a 1 in there, just full proportional control. Saturation, again, this is going to be staying at 12 and negative 12. The plant is set up with your K and your tau values. You can adjust them to the values you found in the experimental procedure within the lab, or you can leave them at the standard ones that the whole class will be using. It's up to you. Band limited white noise, again, to 0. Pulse generator, we can adjust some of these setups. So for instance, I normally would run it at a period of 6 seconds, 25, and then a delay of 2. These are just nice settings for later in the lab. Because I changed it to 6 seconds, you're probably going to want to run it for 6. And the reason for that is that when we open this up and change the view layout, the 2, the things that you have to set up, when you run it, you'll have a nice set of 3 here. Again, this is just the response for the P. A couple other things that I'm going to walk over next are just ways to make it a little bit easier on yourself. So if you were to want to make sure that you have your full Simulink model in view and you say you want to adjust things quickly, one of the important things that I would definitely recommend is to have your scope open on one side. And again, you can do different things like full screen mode and zoom in here. And then open up your signal generator and your PI controller block. That way, when you open up the blocks together, you're able to easily change your values, click apply. So let's say if we change this amplitude up to 100 and apply that, keep the throw in an I gain, just messing around with it at the moment. But instead of pressing OK, which would close it, and I made that mistake just a second ago, we can press apply, and moving on over here, just running the program, and it will automatically run. You come back, change parameters. Another important thing here is to have your cursors. So that's your measurement here. You could do a couple things. So in your settings, you can change it so that you're looking at two different waveforms. In our case, we're going to be looking at the sum one or sum, and so these are the different settings for that. If you set it to that, then you can measure things like the steady state error in this particular case. Oh, I guess I should also mention that you can change different settings to make your plots a little bit easier to read, if it's really up to personal preference, but especially when you output it to make yourself to make your life a little bit easier. You don't want to change some of these things around. So I'd change these to with black. If you look at an active display, you can change the colors of things. And so that's just sort of the idea. You can do these little things and do things differently. I'm going to move back to the one that I fully developed, and they look pretty good for the next portion of this. So the next step of this procedure is going into looking at a PI controller and sort of qualitatively and analyzing how it works. So to start off with, going through the procedure, this is section 2, and I'm just going to start off with just the pure proportional controller. We can go in here and start setting some of the defaults. So we're going to have an amplitude of 50 radians per second and an offset, and a frequency of 0.5 hertz, an offset of 100 radians per second. We'll go into the PI controller, set the proportional to 0.5, set the integral to 0, keep the set point weight at 1. If it's not already 1, turn it to 1. Apply your settings. Moving back over, the saturation block should be in default 12, -12. The transfer function block should not be changed, and it shouldn't be changed throughout the entire lab. These two should stay at default, so I'm going to open them up just to double check. We have 0 noise power, and then the disturbance is also at 0 amplitude. The scope is set up so that when we hit run on that, we can sort of see our responses there. And so the next step after this is to actually start incrementally increasing this value. So we'll go to 0.75 and run it then, and sort of just analyze what's happening. So make some observations, and you might need to do some measurements if you want. If you do want to take a measurement, I want to open that up again and look at, you just press this little measurement button here, and you can go to the trace selections, but it's easier to just go straight here to settings and select your sum and your omega, or your sum and sum 2, and set your time to the same so that you can do those sort of measurements. So now that you've gone through and done the pure proportional controller, we're going to go on and look at a pure integral controller. So this is the sort of setup that you're probably still in after finishing the pure P control. So with that, we'll start by changing the settings. So the signal generator is still going to be at 50 and 0.5 for the amplitude and frequency respectively. The Simulink model offsets there at 100, and we're going to change the PI controller to have a setting of 0 for P and 0.05 for I. And then when we run that, we can see the this response of just a pure I controller. And obviously it doesn't look overly amazing, but just observe what's going to happen when you move it up to your next increment of 0.25. And when you run that, again, your responses are going to change. You can see and observe and make note of what happens. And just a reminder, just make sure you take screenshots and just sort of take some notes so that when you make your report, it is really helpful to include figures along with the rest of the work. Next up, we are moving on to the qualitative analysis of the proportional and integral controller, or just PI controller. Again, the settings for the signal generator are going to be a really simple 50 radians per second, frequency of 0.5 hertz, an offset of 100. And then looking at the PI controller, we're going to start with a 0.1 and a 0.5 for the P and I. And then when we run it, we can see the response. And next, we're going to just sort of analyze and change the KP up and down, and same for the KI. And again, you just observe what you're seeing, make notes, and take screenshots. Moving on to the next section about manual tuning, we're going to be looking at the Ziegler-Nichols method. And there's a good walkthrough within the procedure, sort of about what it is and how you would sort of theoretically find these critical values or ultimate gains. Unfortunately, within the simulation, it is really hard to find oscillations that occur. So in this particular case, we are just going to be providing you with the critical gains and critical period for the proportional controller, which you can use to determine what the appropriate gains are using the Ziegler-Nichols method. So to start off with, again, just sort of as testing, when you go through and calculate your KPC and your TPC, you will get values, and in our case, they're going to be 0.164 and 1.14. Double check it for your calculations. And again, your signal inputs are the same. And when we run the response, we can see a pretty critical response. So either a slightly overdamped or just critically damped response. And that is the ideal for using the Ziegler-Nichols method. The next step within the Ziegler-Nichols is to adjust your gains around a little bit and just see if you can create that slightly underdamped response while remaining unsaturated. So what's unsaturated meaning is looking at the lower response here. In this particular case, we are actually saturated. So try to adjust your parameters using intuition to sort of keep it under the response here, but also provide a slightly underdamped response. And then again, summarize your results, take some screenshots, and explain why you did what you did. And then the next thing we're going to be looking at is the set point weighting. And so in order to just sort of do this, you're just going to adjust BC and see the response. So in our case, it's set to 1, BSP, I mean, it's set to 1. We can decrease that to, say, 0.75 and observe how the response changes. So you can see those adjustments. And just, again, make your observations, and that's about all you need to do. The next section of the lab is to look at response parameters. So within the lab, pre-lab, you went through and did some theoretical calculations to determine some particular gains that will provide an ideal response. So that you did that in section 3.5.1, and the first one we're going to be looking at is question 10. So the first step is to just set those gains to what you found. Hopefully you got the right ones. So for the KP, it is going to be 0.0995, and for the I, it is going to be 1.12. and we're starting with that set point rate ESP of 0. Now we can take a look at the response and make some notes. Go in there, measure the settling time, how long does it take to get to 2%, and then summarize the results. Next thing, you're going to be going in and you're going to be doing the same thing, but with the question 11 results, just verifying that those are also correct. So in that case, you adjust your set point rate up to 0.751 and just check to see what the settling time is and does it actually meet the design. And again, take a screenshot and then summarize some of your responses. In this next section, we're going to be looking at changing waveforms and how we can track it using a PI controller. So to start with, we're going to be looking at a ramp signal. So in that case, we're going to be setting it to a sawtooth waveform with the offset being at 100 still, amplitude of 50, frequency of 0.5. Moving on to the PI controller, we're going to be adjusting the parameters so that it's just a pure integral controller to start with. So that's a 0, 1, 1 for the parameters, and looking at the response. And after seeing that response, we're going to adjust the values. So in our case, we're going to be increasing or decreasing the KI, and specifically looking at how that increase or decrease adjusts the steady state error. So if you grab a measurement in between those two, you can fairly easily determine what the values are. So just sort of experiment with that and see what will happen when you change those. The next step is to go and look at what happens when you do a pure P controller. In that case, this is going to be a 0.1, and this is going to be 0. And then when we go back and run it, we see a very different response. Make note of how it is changed and how adjusting your KP changes it. Again, following through the procedure. Next step would be, once you find a reasonable P number or whatever, you move on and change it into that PI controller. So throwing in the 1 for the KI, we can go back and take a look at the new response. Big thing is just make some observations, play around with the parameters to see what changes and what improves or doesn't improve. In this next section, we are going to begin by tracking a sine wave and then analyzing the phase shift and how it changes when you change your different parameters. So we're going to start by ensuring your system again is set to all default values, but we're going to be adjusting the signal generator to be a sine wave. Still at 50 radians per second, the frequency of 0.5 with that same 100 offset. When we apply that, we can go in now and set the parameters for the proportional controller to be those that were found using the Ziegler-Nichols method. Run the simulation and take an observation of what's happening. As you can see, there are 2 sine waves and seeing some sort of effect here or there. So the big thing that we're going to be doing is zooming in pretty close to the peaks of it, going in and taking a measurement to try to figure out what the phase shift is. But once you find that shift, you can take this delta t value and determine what that is in radians, considering the frequency of 0.5 hertz. And then the next step is to go back and adjust some of these gains and see what happens when you increase or decrease these values. What is the actual effect? Make sure you take note of that, take some screenshots, and justify your answers. The final section within the lab has to do with responding to disturbances. So the goal of this section is really to just test and observe how closed-loop control systems can respond when a force disturbance affects the output. So first thing we're going to have to do is actually start by adjusting some of the parameters so that we can have a steady response. So in our case, we're going to be setting the signal generator amplitude to 0. It doesn't really matter what the waveform is, but it's square wave. And then set that offset to 100. And then to start with, we're going to be looking at a pure proportional controller. So we have our proportional controller set to 0.1. We have our interval set to 0, ESP 1. And then opening up the scope, we have the response. As you can see, when there's no disturbance, there is just a large steady state error, but it is pretty standard. But when we go in, the next step is to actually go in here to the pulse generator and introduce an amplitude. In this case, an amplitude of 50. So if you go and presumably negative 50, 50 will do the same response. But negative 50 is almost like grabbing onto the motor and applying a torque that decreases the velocity the angular velocity of the motor. Keeping some of these settings to the period of 6, pulse width of 25 to 2, technically doesn't make much of a difference. But when we go in and look at the scope, when we run it again, you can see that there's actually a little bit more interesting things happening. So when there's a force applied to the system, you can see that it deviates a good chunk, and then the proportional controller is able to respond to that. However, as you can see, there's still a steady state error, and this effect increased that steady state error. So try to adjust the gain up and down and see how that affects the system and see if it works. Moving on, once you take notes of that and take screenshots, you can move on to the pure integral controller, in which case we have a kp of 0 and a ki of 1, DSP of 1 as well. And in this case, we can see that we have no steady state error, but then when the disturbance occurs, we can see that the immediate change and an ability to react to that, and then the ability to react when it's gone. So make note of what happens there and see what happens when you change the parameter around. Finally, we're moving on to the ability for a PI controller to do the same thing. So setting the proportional controller gain to 0.1 and then the KI to 1, DSP to 1 as well. We can go back and observe the response for that. Take some notes, take a screenshot, and sort of recognize what's happening. You might want to look at the speed that it responds with, take some measurements. The important thing is that you can see what happens when you adjust these parameters. What happens when you increase or decrease the proportional gain. Next, go back and actually plug in some of the values that you got for KPKI from your different methods throughout this lab procedure and verify that they work, and is it a good choice for low disturbances in this case, and how does it compare to the others. So just sort of include plots of each one of those and make notes, justify your answers, and hopefully you learned a lot from doing this lab.